Perfect. And now I would like to introduce Kato-san, who's come here from Tokyo to talk with us about Autoware. I think you're going to find this fascinating. He's also a professor at the University of Tokyo. If you like.
What's this? Hi. Good morning. Morning. My name is Shinpei Kato from University of Tokyo. I also represent my startup, which is called Tier 4. So today I'm happy to be invited here to present Autoware, which is a 3 years old open source project. So I'm going to introduce how we use open source software for self-driving. So Autoware is open source software for self-driving, not only on your desktop, but also in a real car using a automotive specific board. So we actually use this software by ourselves as well for a lot of field testing. We equip the facilities such as small computers, network switches, batteries, etc. And Autoware is installed and control the car in terms of, so the car is modified to receive some commands from the computer. Then the Autoware is kind of a brain for the self-driving technology. So it sends a command how the car should move. Let me introduce a couple of examples or use cases that we use Autoware for. So this field test is performed by our team in Japan. So our team is qualified to operate driverless car on a public road. So this is actually legally performed. So we have a authorization from the police and the government to operate the car without drivers, without violating the law. So it's kind of complicated mechanism, how to make it happen, because still a driver with a driver license must be ready for taking over the car in remote place. So the remote place is always connected by LTE. But once such mechanism is constructed and permitted, then we can make a driverless car operation in Japan already. But driverless car in service will still take some time to be deployed. So today, the most common example of field testing is we still have a safety driver sitting in a driver's seat, because if some accident happens, then the driver can immediately take over the car control. So in this field test, the driver still sits in the car driver's seat, but everything is automated. So from city to highway and heading for the airport. So this scenario, this car is heading for the airport from the city through the highway. And this is how the car understands the real world. So in 3D structures, and the green highlighted line shows the path that the car tries to go forward, and some tracks or objects are kind of captured by a laser sensor. Then if you see some numbers on the line, it is a planned velocity. So the car always tries to follow the velocity planned on the line. Actually, this type of field test, I believe now, it is happening in everywhere in the world. In Japan, yes, maybe our team has the most experience, but also other companies are now trying to do this type of demo. And in Europe, in the US, and Asian countries, I see a lot of self-driving field testing using such a modified car. But as I mentioned earlier, I believe it still takes some time to be deployed. Perhaps the first commercial autonomous car will be showing very soon, but it's just going to be the first set of the cars. It will still take some time to be deployed. But yes, in terms of technology, if we try this, say, 10 times, then we could do this 9 out of 10. But still, the problem is that how to handle when the car fails. So in order to deploy the technology, we can't reach 100%, but we have to reach maybe 99.9%, and the rest of the risk should be covered by insurance or social approaches. And we also have already potential passengers try on the ride, because okay, give me a moment. Okay. So this is another example of field test, but assuming some particular services. So this is a demo with Japan Post, which is a kind of government-supported posting services in Japan. So we actually engaged with Japan Post teams, and this car is actually supported by the Japan Post. So it is now delivering some postal boxes. It is heading to some branch of Japan Post. However, stopping by several sub-branches. So now this car has 2 boxes. It's just for demo. And it's actually central of Tokyo. It's a very crowded place, but everything is automated again. And it tries to stop by a sub-branch. Then it wants to get one more box. This operation could be done by a human. So a human is standing on the branch side. Then once the autonomous car arrives, then it delivers another box. Then the car just restarts the operation again to head for the next branches. So as you can see, there are actually real traffics and multiple lanes. And since this car has to go on right turn in the next few moments, now the car is trying to make a lane change to the right, because in Japan, you can't make a right turn from the center line. So this includes a lane change, but now the car cannot find the opportunity to make a right turn, so it is waiting. But finally, perhaps once the space is found, then the car is going to, actually it's made a right turn. So this operation is done at about a 30, 40 miles per hour. So perhaps this is kind of upper bound that we could provide kind of real services using our open software. So spending more time, we could provide perhaps higher velocity services, but today 30 to 40 miles per hour would be some upper bound. And we also do similar testing in US or in Europe, so many other countries. So that's also very advantage of software. So our software is used in many countries, not only in some particular countries. And the types of the cars, we also don't stick. So on one hand, we could use OEM cars, but on the other hand, we could also use a small EV. So this is actually manufactured by our team as well. Because I believe that a deployment of autonomous cars could start with small cars. And it is also interesting to see that in car services, when you try our car, you can also get into virtual world, because we are now thinking about not only automation, but also how to spend your time in a car. So this is a virtualized world, but the motion of your virtual world is aligned with the real car motion, because our autonomous car understands the motion of the vehicle very precisely, so it can be reflected to the motion in the virtual world. This actually is a pretty important aspect, because if your motion is not aligned in the virtual world, you may feel sick. So in order to avoid kind of feeling sick in kind of services, it is actually important to align motions in real world and virtual world. So, and we can also switch between virtual world and augmented reality. So it's going to be one of the way that how we can spend time in autonomous car. By the way, this services right now today is demonstrated in a Tokyo Game Show in Japan. So, and I think we're going to get a lot of attention now. So yes, and a couple of other examples that we test our software. So this car is actually 3D printed. Now the car can be 3D printed and on top of a golf cart. So this is golf cart, but we remove the body from the golf cart, and instead put our kind of handmade 3D printed body on top of the car, so that the car looks very different. I believe that just using golf cart may not give you user experience, but changing the appearance actually affects a lot to the services. So this appearance, I believe that in the future, 3D printers or some kind of handy methodologies to build the car could be deployed very soon. And yes, so in any car, you can fall into the virtual world and change the contents. However, in this case, you can, again, next to your place, you can have a dating, etc. So virtual reality and autonomous cars, I think it's a kind of synergy, technology, because you can always change the space and time in autonomous car. If you don't use virtual reality, then you always stay with the real world, which doesn't change. But virtual world, you can change depending on your demand. And for the smaller cars, we also support. So this is actually wheelchairs. Again, we replace the body of the wheelchair with the 3D printed ones. Then it looks like a delivery robot. So wheelchair, golf cart, they already deployed EVs in the world. We don't have to develop new cars. We can use existing car platforms, but using 3D printers, for example, then you can change how the services could be accepted by the society. And yes, another virtual world. So actually, the appearance of the car can be changed by 3D printers, and the experience of the autonomous car can also be changed by virtual reality. So Autoware is not the software that only supports autonomous driving function, but can be connected to kind of virtual reality services or some other related technologies. So it's open source. If you go to website, so Autoware.ai is kind of information website. So you can also access a lot of tools which can support Autoware. Then there is a link to the GitHub. Then you can finally download the source code. So now we have close to 2,300 starts. Since this project is still 3 years old, I think this is a good number. And now it's increasing every day. So I believe that Autoware is going to be one of the standard software for self-driving technology. It's a bit difficult to explain what functions Autoware provide, but I would say mostly all functions that are necessary for self-driving, Autoware support. But some functions are very high quality, but some other functions we still need improvements. But once again, since all the necessary functions for self-driving are already covered, so a lot of R&D purposes actually using Autoware, since you don't have to kind of prepare for individual functions. Once you download Autoware, you have basically everything. Now it's up to you what functions you like to improve or what functions you like to replace with your own algorithms. So as a platform perspective, Autoware is actually very useful since everything is integrated in a package. Okay, so let me introduce how actually technically Autoware works. So before you run Autoware, in fact, we need some particular data set which is called 3D map. 3D map is you have to run kind of special vehicle instrumented with some expensive sensors, but once you run that sensing cards, then you get scanned data of the place where you want to provide autonomous car services. This is not a kind of movie. This is a 3D points, collection of points, which is often called point cloud. So it's a collection of XYZ points with RGB information. Having this, you could understand how the structure of the place where you operate your vehicle look like. But we have to do some other post-processing, which is to extract the information from that structure information. Because like intersection information or lane information or traffic light information, those information actually is static. It doesn't change. For instance, the place of the crosswalk doesn't change tomorrow. So we like to extract the static information as much as possible before you operate autonomous car so that you can reduce the computation requirement in real time. So once you extract the information, static information from the kind of 3D structural data, finally you have a kind of high definition 3D map, which includes structural data and semantics. Semantics means where is the lane, where is the crosswalk, where is how the intersection is constructed, road paints, buildings, traffic light signals. So those pieces of information all integrated with the 3D structural information. So this, we often call it high definition 3D map. Autoware doesn't actually work without this 3D map data. So having 3D map data is essential for Autoware. But in other words, if you have this 3D map information, then Autoware can, mostly in all places, can provide an autonomous function. So the first significant function that Autoware provides is localization. So Autoware assumes that the car has a laser sensor in 3D capabilities. So having 3D sensors and comparing the scanned information with the 3D map data, both data sets are represented by 3D structural information. So we can actually make a matching. If the car is in a place where the 3D map is provided, there should be one unique place where the shape of the laser scan and the 3D map shape are matched. So we compute this process in real time every time the sensor information is updated. So you can see that the red arrow represents the place or position of the car estimated, which is not a log. It's estimated by computing functions. This accuracy of positioning or localization is a few centimeters. So this means that our autonomous car always understands the position of the car over the world by a few centimeters accuracy. That's why Autoware is now kind of acceptable for the city operation. If the accuracy of localization is not a few centimeters accuracy, then autonomous driving in city would be difficult. And kind of this is supporting function. So if you know your position very accurately, which means that you can also build a map. So this is kind of complementary to each other. If you have a map, you can make a localization. If you can make a localization, you can make a map. So this car, ahead, you don't have any map data, but because the car now has a localization performed, so it keeps saving the scan data. So the car itself has a laser scan sensor. So if the car goes to some place, then the shape of this place can be saved. So accumulating this scan, then we can finally acquire the 3D map information. So if you have Autoware, you can also build a kind of rough 3D map. But as I mentioned earlier, if you want to get very kind of precise high definition map, then you need a kind of special car, which is equipped with some expensive sensors. But Autoware itself is also capable of constructing a 3D map. And perhaps this is the most popular area of autonomous driving, so computer vision. Every year, new deep learning algorithms are presented in a conference. So Autoware always tries to update the algorithm. Like 3 years ago, we had SSD, but last year, Euro 2 came up. Then this year, Euro 3 was presented. So the community of Autoware always try to implement new algorithms so that R&D purposes, you can also access the new algorithms in the actual platform. And so object detection also, there are multiple ways. Like you can use cameras, but the cameras doesn't tell you the distance information. So now there is the sensor fusion. You can tell what it is by camera, but the distance information can be provided by a laser sensor, so which is called sensor fusion, using different sensors, then producing richer information. Path planning, so we have a Dijkstra or A-star-based. Once the object is detected, you can calculate a kind of avoiding route in real time. Or another algorithm is that you already have predefined avoiding path, and you can just choose one in real time. So this is very different. Calculating the path in real time or pre-calculated path, you just choose one in real time. So there are many other algorithms for kind of path planning, but we try to support as many algorithms as possible. So all those pieces of functions can be all performed in real time by using a one single computer. We often use another computer for visualization, but basically every function can be supported by a single computer unit. This is a case of NVIDIA Drive PX. So you just launch the system. So everything is running on a single computer unit. So we can install a 3D map data and make a localization and draw a path. Then intersection, you detect the objects and make a decision when a space is clear, then you can resume your operation. if something is ahead of your path, then you can recalculate the route and try to avoid it. So this basic function already provided. So when you download Autoware, you can start here. But this is a controlled area, it's a driving school. If you go for a public road, then actually the scenes are very different. So even though Autoware could work as you expect in a controlled area, but for public road services, you need a lot of improvement. So the current status of Autoware is, actually we don't guarantee any real-time performance. The whole pieces of demos that I demonstrated today, we tried it, then we could make it. But we didn't know if it could be made before we actually tried. But in order to make a production, you have to make service quality, like especially we respect the real-time performance. So at least the system should be able to be analyzed statically. So now what we're doing right this moment in the research team is that we try to make a system model representing the system by a graph. Because if you see left bottom side, the Autoware is composed of more than 200 tasks. And those 200 tasks have input and output. Then there are data dependencies each other. So for instance, object detection function can never start unless the sensor information arrives. So those data dependencies actually make it difficult to analyze the system in real time. So we like to make a system model of the autonomous car, which is Autoware, so that we can make a real-time analysis, so that like a timing constraint could be guaranteed beforehand. We actually operate the car. So this is what we're trying to achieve in the research phase. So like a scheduling problem is a kind of academic research area. But we know that a lot of algorithms from academic research area would be useful to realize this kind of analysis. Okay, so this was a kind of overview of what is Autoware and what we are doing using Autoware and what we plan to do in the research area. It was actually a lot more that we are today doing or we plan to do, but I appreciate we can maybe chat offline and make more deeper discussion and collaboration. Okay, that's it. Thank you.
Thank you so much, Kato-san. Do we have maybe one or two questions? Anybody have a question? I know I can think of a bunch of questions. Anybody? Question?
The module that you have on the top of the car, does the open source site also put together a design for that?
Yes.
Okay, and how much roughly does that cost?
So it depends on sensor performance, but from 10K to, but you can get up to 100K if you choose a very expensive sensor set. But it's actually 10K. So from my experience, 10K for a sensor kit for autonomous driving has made a significant leap as compared to a few years ago. A few years ago, there was no choice of 10K, always 100K. But today, the cost of sensor is also very decreasing. So I believe in the future, it's going to be less than, say, 5K or a few thousand bucks.
Is that the LiDAR, the LiDAR sensor?
Yeah, I'm talking about LiDAR sensor. But it's a whole sensor kit would also be going to be very cheap, reasonable.
If the Autoware is dependent on the point cloud 3D generation models, I mean, can't that be kind of can't that compromise security of the vehicles? How often do you have to generate these images? And I mean, what if like a building goes up or goes down or streets are modified?
Yes, that should be also analyzed. But from my experience, you could just make an update every year. You don't have to make update every day or every week. But this means we shouldn't make an update every day. So my personal perspective is that at least maybe we should be able to update every month, if not needed, but every month update would be most reasonable because everyday update could be very kind of costly, expensive, so every month. But in reality, from our experience, the map can be used for maybe for 1 year because only a few buildings gone, it doesn't really affect the performance of localization. So basically, 1 year or 2 years duration is acceptable, but we aim for map updating every month.
So I have a quick question for you. What about connectivity? So the car operates independently by its own, but is there connectivity to the cloud? And in the future, will there be benefits to having connectivity between autonomous cars?
So if you go to the website, we also have a AMS, which is Autoware Management System. So if you have Autoware and have a connectivity like LTE, Wi-Fi, anything, then you can watch the whole Autoware cars on the browser. So the position or the status of the car can be, yes, managed by cloud. We also provide that tool for free.
So will cars communicate with one another?
Not direct, but yes, going through the cloud, yes, you can exchange the information. So for instance, the car behind the building, which is not captured by the sensor, you can also make it visible going through the network.
Thank you so much for coming here. It was fascinating, really interesting. We really appreciate it.
Thank you very much.